Hello everybody. Sorry for the late video. I don't know when this will be posted, but hopefully y'all have this before the weekend. So, um, the next topic I wanted to cover is computer floating point operations. I know a lot of students struggle with this one just because there is a lot of steps to do. So, yeah, let's go ahead and get started already. So the first thing I'm gonna go over is decimal to hexadecimal conversions. I'll kind of explain my process and everything that happens. So feel free to rewind, rewatch if you ever get stuck. So yeah. All right. So first we're gonna do decimal to hexadecimal, and the first example I have is 193.218,750. Okay. So the first thing you need to understand about the structure of IEEE is how the binary is generally laid out. So how the binary will be laid out is it'll first have the sign, whether it be negative or positive. It'll have the exponent and then the mantissa. So the first thing we can easily derive here is the sign. We know that it's going to be a negative number since there's that negative in front of it. So we already know that the sign is going to be 1. So if it was a positive number, we would make it 0. But in this case, it's a negative number, so we can leave it as 1. Unfortunately, we cannot get the exponent just yet. First, we need to derive the mantissa. And the way you want to do that is we'll take this whole number here, and let me make a different color. So we'll take this whole number here, and we want to convert it into binary, right? And the sign doesn't matter. We're treating this as if it's unsigned, since we already denoted that it was negative over here. So we'll take 193 and we'll just do our division method that I've talked about before. So yeah, let's do 193 divided by 2. That should be 96. And that would be 192. And you're gonna have you'll be permitted to have a calculator on the test, and I think even it would almost puts a calculator embedded in the quiz, so you'll be okay. Like, don't be too worried if you're worried that you can't do like big off the top calculations like that in your head. You'll be provided a well, you won't be provided a calculator, but you can bring one. Okay, so next thing I'll take the quotient. I forget what it's called, but we'll take that and then we'll divide that again. Again, this is just doing the division method that I've talked about before. So this would be 48. 48 divided by 2, that's 24. This would be 12. This would be 6. This would be 3. This would be 1. And then finally, that's going to be 0. Okay, so that's our first half of the mantissa. So we can go ahead and write it from most to least significant bit. So that's going to be 1, 1, 0. Oops. Sorry about that, you guys. Okay, so that's the first half of the mantissa. The next half we want to work with is the decimal part, right? And that's going to go following this first part, which was the whole number, right? So the way we're able to convert this decimal part into binary is we'll do the opposite of what we did before. So for the whole numbers, we were dividing by the base 2. But now for the decimal numbers, the not whole numbers, instead of dividing, we're going to multiply by 2, right? So we'll take, what was it? I think I have it written down here. We'll take 0.218750, right? And that's just this lower half here. We'll take it and then we'll multiply it by 2. Okay, so 0.21875 times 2, that's going to be 0.4375. And the bits that we're keeping, because before we were looking at the remainders here, and that's the bits we were keeping. But now instead, we're going to look at the first whole number bit. That's going to be the bit we will keep and remember. Okay, so next things next, we'll take this number here and we'll also multiply that by 2. Okay, and that times 2 is going to be 0.875. Again, that's another 0, so I'll write that up here. Okay, and then I'm only taking this lower half here again. Okay, 0.875 times 2, that's going to be 1.75. Okay, so that one we will write up here. And now, remember I said we're only taking this lower half. So we're not going to multiply 1.75 times 2. We're only going to multiply 0.75 times 2. And of course, that's going to be 1.5. So I'll write the 1 here again. Okay, and then again, I'm only taking the decimal part. So this is going to be 0.5 times 2, which of course is 1. And now I have a 0 here. So now that I have a 0 here, if I keep multiplying by 2, I'm only ever going to keep getting zeros, right? So we can just assume that these zeros are going to repeat for the remainder. So, wait, did I write that down? Okay. So we should have another one here because of this, and then a 0. And then we'll make that little bar so that we know that it's repeating. All right. So there you go. That's your mantissa for now. The next thing we need to get is the exponent, right? And how we're going to do that is we'll take the decimal part and we'll actually, let me make the exponent a different color. We'll make it blue. So we'll just count how many times we need to move it over to the left until we get to the most leading bit, right? So that would be 1, 2, 3, 4, 5, 6, 7, right here. So we'll go all the way until we get to that first one. So I'll just mark it down here. 7. Okay. Now that we have how many times we were able to move it, we're going to take that number and we're going to add the bias. The bias is 127. Right, so 7 plus 127, the bias is going to be 134. And the bias is just referring to the range of numbers. Okay, so now we can get 134 and we can convert this to decimal so that we can get our proper exponent that we can write down here. Okay, so 134 divided by 2 That's going to be 67 at first. And this is going to be 33 right here. That's going to be 8. This is going to be 4. Oops. And then finally we get that 0. Alrighty. And the exponent has to be 8 bits. It has to be 8 bits. So we'll just write that from right to left. And then just verify that you have 8 bits there. I think I wrote this wrong. There you go. So it should be 1, 0, 0, 0, and then another 0, 1, 1, 0. Yeah, perfect. Okay. And this is 8 bits, so that's correct there. Oh, and I did forget to mention right here, after we've moved the decimal, we can actually just drop this one. So this one is not to be included. So please don't forget that. If you include this one, your whole answer is going to be messed up. Okay. So that being said, let's go ahead and write everything together in binary. So like I said, sign is going to go first. And we made sign, well, we made sign red, but I'll just write it all in black. So sign is going to be 1. Exponent, we said, which is over here. And again, we did that by counting how many times we had to move the decimal point to the most leading bit there. And then we added the bias, which is 127. And then from our sum, we convert that into binary. Right. Hopefully I'm not losing anybody there. So now I can just get that binary I got, which is 1, 0, 0, 0, 0, 1, 1, 0, right? So that's all of the exponent. And now I can write the mantissa. The mantissa we got by taking that whole number, doing the division method, converting it to binary. And then the lower half, we did the opposite. Instead of dividing, we multiplied it by 2 and then got that leading bit here, the whole number here. So yeah, let's go ahead and write that down. Don't forget, we're not including that 1 in front of the decimal point. So that's going to lead up being 1. Oh, let me zoom out, please. Okay, so that's going to be 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, and then the rest of the zeros repeat. So the thing is for floating point, we need 32 bits in binary, so that way we can get the correct amount of hexadecimal digits. Oops. So let me just, so that should be 1, 2, 3, 4, 5, 6, 7, 8. So in total, we should have 8 hexadecimal digits, right? So how we'll do that is we'll just divide everything by 4 bits, right? Okay, and then we'll just convert this binary into hexadecimal from here. So Again, let me use a different color. So this is going to be 12 because this is just 8 plus 4. 12 in hexadecimal is C. This would be the same as saying 2 plus 1, which is 3. This is just 4 right here. This is 1. And then this is, again, this is 3 because this is 2 plus 1. And then, okay. So remember how I said we need 8 digits in total? So far we only have 5. So we know we can just pad the rest with zeros. So that would be 5, 6, 7, 8. Okay. All right. So this would be the same as saying 8. And then this would just be a 0 and a 0. Alrighty. So that is your answer for that question. And hexadecimal is denoted like this. So you put that 0 and then the X and then the hexadecimal number. So yeah, that's how IEEE is represented. Okay, yeah. Okay, oh, and also let me denote this. And then this would be, all right. So yeah, that's how you do decimal to hexadecimal. We'll go ahead and do another example of this as well. But yeah, that is exactly how you do it. Those 3 steps. Remember, we have sign, exponent, mantissa. Okay. Let me go ahead and get another example for you guys ready. Um, mm -mm. All right. So the next example I want to do is going to be a positive number this time. So I just realized that I wasn't even sharing my screen. So I actually did the second problem without even showing it. But sorry, let me just get my OneNote to start acting right. Okay, so this is the problem I did, and it didn't happen to get recorded, which is really frustrating, but I'll just kind of go over it. Um, Sorry I wasn't able to do it step by step, but it's the same process, really. So let me explain it. Okay, so the example I was going to work with is positive 162.75000. The first thing we can deduce from this is the sign. So we don't have a negative sign, so we know that it's a positive number, therefore we know that the sign is going to be 0, right? All positive binary numbers, they start with 0. Okay, so then afterwards, we can't get the exponent right away. We need to get the mantissa in order to get the exponent. So I took the whole number, 162, and then I just kept using the division method until I got a 0 on top right here. So 162 divided by 2, that's 81. 81 divided by 2, that's going to be 40, remainder 1. 40 divided by 2, that's 20, remainder 0. 20 divided by 2, that's 10. 10 divided by 2, that's 5. 5 divided by 2, that's 2. Well, it's 4. And then we get the remainder 1. 2 divided by 2, we get 0 remainder. And then finally, we got the 0 on top here when we divided 1 by 2. So I took all of our remainders, wrote them from right to left. I wrote them down here, right here, which is 1 0 1 0 0 0 1 0. So that's the first half, the whole number bit. Then I went ahead and took the decimal, and I did the same thing where I just multiplied it by 2 every time, and then the first bit before the decimal is the bit I wrote down following our whole number in the mantissa. So 0.750000 times 2 is just 1.5. Then I don't multiply 1.5. I only multiply the 0.5 that we got from here by 2. That gives us a 1. And then now that we have a 0 here, we know that every time we just multiply 0 by 2, we're just going to keep getting 0. So we can write that as we can write that bar over it to show that it's going to be repeating. Okay, so now that we have our whole mantissa, we can get our exponent. How I did that was, again, I got the decimal point and I moved it as many times, and I counted how many times I needed to move it until I got behind this most significant bit over here. Right. So that's 1, 2, 3, 4, 5, 6, 7 times. So the decimal would go here, and then I could just drop that leading 1 now. Okay, so since I moved it 7 times, I went ahead and added 127 to 7, 127 being our bias again. Please don't forget that. Then I got 134, and that's the same we got over here. So just to save time, I didn't do the division process. I just got our answer from here since it's also 134. All right, so then you have, by that step, you'll have all the components you need. You have the sign over here, you have the mantissa over here, and you also have the exponent over here. So you want to write it in order. Sign, we said it was positive, so it starts with a 0. Exponent, that's 8 bits long. We took that and we just wrote that here. And then the mantissa minus that leading 1 goes down here. Right, and then I just padded the remainders with zeros because we know that the 0 just keeps repeating. Then you want to divide this big number into 4 bits, sections of 4 bits. And then using those 4 bits, we can convert them into singular hexadecimal digits. So this is the same thing as saying 4 because it's in the 4th place. This is the same thing as saying 2 plus 1, that's 3. This is 2. Again, this is 2. This would be 8 plus 4, which is 12. And 12 in hexadecimal, that is C. And then the rest are just zeros. So yeah, that's the answer for that example right there. Sorry I wasn't able to record it at first, but hopefully my explanation helps. So yeah, don't remember do remember the steps you gotta take. So yeah. Well, actually, the sign would probably be step 1, the whole number step 2, decimal number step 3, and then exponent would be like step 4. But I'll just write 3 for simplicity's sake. And then afterwards, you put all the binary together from sign, exponent, mantissa, and you just convert it into hexadecimal. And if you guys are still stuck on conversions, I recommend you watch my previous videos because those explain every conversion method, basically. Okay, so yeah, that's that. So finally, we can go ahead and just move on to the next example. So actually, for the next example, I want to work with the same number, with this same number and prove and show you guys how we can work backwards. So we'll take this number and then we should get this number, right? We should get negative 193.218750. Okay, so I'll show you how to do that. So let me just rewrite it. The 0x just is the representation of the floating point, IEEE. So I'm writing each hexadecimal digit and I'm giving them 4 bits each. Because a singular hexadecimal digit will be represented by 4 bits, right? Okay. Let me just make sure this is the same number. Yep. Okay. I'm gonna move this to the side so that you guys don't get confused. Okay, so from here, now that we divided each singular digit into 4 bits, we can just convert it into binary straight up. So C, we know that C is the same as 12. So that would be 8 plus 4. And 3, that's going to be 2 plus 1. 4 is just that 1 4 place right there. And then 1 is just that last bit. And then again, we have 3. We have 8. And then the rest are just zeros. Okay. Yeah, and please, if you guys aren't this comfortable with just converting hexadecimal straight up to binary like this, like it should be very intuitive for you by now. Just go back to the other videos and watch those conversion methods again, right? Okay. So that being said, now we have our binary number, right? So we can go ahead and start sectioning them off based off of sign, exponent, and mantissa. So the sign is the very first number. And since this is a 1, we know it's going to be negative, right? And that's right because and remember we're trying to get this number again, and that's a negative. All right. And then the next 8 bits, or 1 byte, again, 8 bits is a byte. That's going to represent our exponent, 3, 4, 8. So all of that is our exponent here, and I'll go ahead and just rewrite it again. All right. So now that you have your exponent, you'll want to convert it into decimal. So this would be the same as saying 128 plus 4 plus 2. And that's going to be 134. And then that's not the number we want, right? We still need to subtract our bias. And that's going to give us 7. Okay, so yeah, over here, I was adding our bias to the amount of times we were moving because we were trying to get to binary, right? But over here, we're trying to get back to decimal. So instead of adding our bias, we're subtracting bias. It's the opposite in this case, remember? So we know our exponent is 7, so that's going to play a key role later on. The rest we can assume is our mantissa. Or well, we can't assume it is our mantissa. Okay, so I'll write that down here. And reintroduce that one back in. Remember over here in the previous examples, we got rid of that one. So when we're coming back from binary to get to decimal, we need to reintroduce that one. Please don't forget that. If you forget that, your whole answer will be messed up. Don't forget to add the one back. And then I'm just going to copy the rest here. So I already have 1, 0, 0. So the next is 0, 0, 0, 1. Okay. And then 0, 0, 1, 1, 1, 0, 0, 0. And then the rest are just zeros. Right? Okay. So we had our decimal right there. Remember, that's the one we add back in. And since we have our exponent, now we know how many times we need to move the decimal back. So now I can move this to be 1, 2, 3, 4, 5, 6, 7 places behind. All right. Now I can rewrite this as 1, 1, 0, 0, 0, 0, 0, 1. 0.00111, and then the rest are going to be zeros. Okay, so now that I have my binary set up like this, all I really have to do is like that scale position notation method. So over here, this would be 1. This would be 2, 4, 8, 16, 32, 64. And then this one's going to be 128. Okay, so that is all equal to 193. That's a good sign. That's a good sign because remember, we're trying to get this number that we had before. Okay, and now for this part. So when we're adding these, the whole number side, all we're doing is we're keeping track of its position and we're adding those positions together. This would be 0, 1, 2, 3, 4, 6, 7. But over here, instead of raising it to the power to positive powers, we're going to raise it to negative powers. So there is no such thing as -0. So instead of starting with -0, this place right here is actually 2 to the -1 power. And this is just like a fraction. Let me see. 2 to the -1 power, I think that should just be 1/2. Yeah, it's 1/2. 2 to the -2, that's a quarter. And then 2 to the power of 3, I think that's 0.15. Oh no, sorry, that's 0.125. It's a fraction. And then this would be to the power of 4 and then to the power of 5. And remember, we're only looking at where the ones are. So this would be equivalent of saying 2 to the negative power of 3 plus 2 to the negative power of 4 plus 2 to the negative power of 5. And you can just plug that into your calculator like that, unless you know how to, unless you know what fractions those are. But I think it's just easier if you put it in your calculator. So after I put this into my calculator, I was able to get to 1.875. And remember, our sign we had earlier was negative, so we need to include that. Yep, that's our answer. So this was the answer we were looking for since we were working backwards from this problem. So yeah, we know we didn't do anything wrong here. So yeah, let me go ahead and just re-explain everything. Um, we took our given hexadecimal number, we converted it into binary for each bit. So yeah, each hexadecimal digits gets 4 bits for binary. We convert that just with regular conversion. So C became 12 over here, 3, 4, 1, 3. This is 8, and then the rest are zeros. We know the first number is our sign, and that was a 1, so we said that was negative. The next 8 is our exponent. We convert that to decimal, subtract that by the bias, and that's how we get our exponent. The rest is the mantissa. We reintroduce that 1 and then the decimal point. We move the decimal point over by whatever our exponent was, and then we convert the first half position notation, and then the second half position notation, except we raise it to negative powers. And then you just write all of that together, the sign plus the first half plus the second half. So yeah, that's that one. I mean, let's go ahead and do another example, but instead we won't work backwards. Okay, let me pull one up. Okay, so next example I want to work with is going to be 41EDC000. And again, we give them 4 bits each. And then we just convert it to binary. Okay, so 4, we can just put that in the 4's place right there. 1, just put that in the 1's place. E is the same thing as 14. So that would be 8 plus 4, which is 12, plus 2, that's 14. And D is 13, so that would be 8 plus 4, which is 12, plus just 1. That would be 13. C is the same as 12, and that's just 8 plus 4. And then the rest are just zeros. All right. Our sign this time is 0, so therefore it's positive. Our exponent, let me just go ahead and rewrite that. That's our exponent, okay? And then we'll convert that into decimal, so that would be 128 plus 2 plus 1, which would be 131. Okay, so now we'll subtract that by our bias, 127. Don't forget that. So 131 divided by 127, that's going to give us 4. So we'll know that's how many times we got to move that decimal point over, right? The remainder is our mantissa. Remember, reintroduce that one and then rewrite everything you see there. And be very, very careful. I'll just say that repeats. Be very, very careful because if you happen to miswrite, you forget a digit or something, it affects your answer. Okay, so now since we know the exponent, we know that we have to move this one over to the right 4 times. So 1, 2, 3, 4, 5. Okay, so now I can just rewrite this mantissa entirely. So this becomes point. Okay, and then all of those repeat. Two, three. Oh, I think I moved it too many times actually. One, two, three, four. Yeah, I think I'm good thing I caught that because then I would have got the wrong answer. So yeah, be careful with that, you guys. Luckily, I think you guys should only have like 2 problems, one from hexadecimal and then one from decimal to hex. So yeah, just try to take your time on these ones because they're like very long and convoluted. So now I can rewrite this. And those zeros repeat itself. Okay, so now I can say that this would be 1 plus, this is 2, and then this would be 4, and then that would be 8, and then plus 16. Okay, and then that is 29. And then this part is going to be 2 to the negative power of 1 plus 2 to the negative power of 3, because we skipped that, to the negative power of 4, 2 to the negative power of 5. Okay, so let me put that in my calculator. Okay, and then this gave me in my calculator 71875. And then it's positive, so remember it's positive. So yeah, that's our answer for that one. Yeah, it's right. All right. So that's the end of this video. Luckily there's not, we only work with decimals and hexadecimals for this one. Well, I mean, you do work with binary since you have to convert it to binary first, but there's no other variations, just decimal to hexadecimal and then hexadecimal to decimal. Yeah, so this is a very tricky topic. I know a lot of students really struggle with this, so again, please, if you have answers about anything, I mean, questions about anything, shoot me a message on Discord and yeah, I'll get back to you soon. But yeah, that's the end of the video. Thank you guys.